Good morning, grade 11s. It's Monday morning, May the 4th. I hope you had an enjoyable weekend. To begin with today, I want to start with a little bit of sad news. While I'm recording this on Friday afternoon, and you're going to view this on Monday morning, the sad news is this, that you may have noticed over the past 5 weeks since March 20th, I have not shaved and I have been growing out some facial hair. Well, the sad news is that today is the last day that you will see the facial hair. I need to shave it. At the beginning of this, in May 20th or March 20th, when we let out of school, when in-school classes were suspended, I told my wife that I would grow out my beard until one of two things happened. Either school would resume and we'd be back in classes, or the thermometer would hit 20 degrees. And as you may or may not know, but yesterday on Thursday, the thermometer hit 21 degrees. And so a promise is a promise. I must shave off the beard. And so by the time you see this on Monday morning, it'll be gone. I'll be back to my familiar goatee, and we'll continue on from there. All right. On Thursday, Friday last week, you were answering a poll question on whether or not when a tree fell in the forest, if it made a sound, if no one was around to hear it. And lots of good responses. Thank you all for participating in the poll. The vast majority believed yes, that it does make a sound whether or not you are around to hear it. The correct answer is there's no correct answer. This is something that has been debated since the 18th century. And it really depends on how you want to view sound. Are you viewing sound objectively or subjectively? Now, you do have to take into account a definition of what sound is. Sounds are called sounds because it is an auditory sensation. It is something that our auditory nerve in our ear picks up. Our brains transmit that and into a sound that we hear, that we can recognize. But when a tree falls, when something happens, it creates a sound wave. So objectively, sound waves are always there, right? When a tree falls and it causes a vibration, in air molecules, that is a sound wave, and they are present, yes, all the time. If you want to look at it subjectively, that is that in order for a sound to be a sound, it has to hit your eardrum, and those sound waves have to be converted into an electrical impulse that goes to your brain, and then you hear something that you recognize. Then no, that won't happen, because if there's nobody or nothing around to hear it, there's no auditory sensation in that way. So objectively, absolutely, sound waves are produced. Subjectively, no, because there is no auditory sensation. So you're both right, and thank you for participating in that, and you can continue to have the debate as we go on. Again, philosophers and scientists have debated this since the 18th century. All right, the other thing I want to talk to you about today is the Doppler Effect. You were reading about it on the weekend if you read section 15.1 as was assigned, but we're going to go over to the board and we're going to take a look a little bit more at the Doppler Effect. All right, let's talk Doppler Effect. So Doppler Effect, as you would have read, hopefully, you get a bit of an understanding of what it is, and you've all experienced the Doppler Effect at some point in your lives, I guarantee it. But what Doppler Effect is, the definition of it is an apparent frequency change as a source of sound approaches or moves away from you. And so if you're thinking of where have I heard that? Well, you've heard it all the time. If you go stand out on your street and a car goes by you, you are hearing the Doppler Effect. It's that typical where you have a high frequency as the car approaches you and a lower frequency as it goes away from you. That is the Doppler Effect. And the Doppler Effect can be used in a variety of places. For our purposes right now, we just want to understand why we get those frequency changes and look at a formula that will allow us to find the frequency changes. What frequency will we hear given a certain scenario? And as you heard, I just dropped my marker, so I'm going to go get it. And we're back. All right, so here's you listening for sound. Here is a source of sound that is emitting a source, a sound that is coming out here. And again, I just want to mention to you that in your reading, you read about things like the amplitude of sound, which is the loudness of sound, the amount of energy that's being transferred. You would have read about the frequency of sound, which is the pitch that you hear, okay, higher pitch, higher frequency. You would have learned about the speed of sound. And again, in your textbook, there wasn't really a formula given for the speed of sound, but it was there. It said at 0 degrees Celsius, it was 331 meters per second. And then for every 0.6 degrees Celsius, the speed of sound would go up by 1 meter per second. So on the other board, when we do a question, we'll write down a little bit of a formula for the speed of sound, but it's there. So what we have is we have a source here that's emitting a pulse, okay, a sound that is coming out of it, and the sound waves are leaving from it, and the sound waves, as they leave my voice, they go around, right? They come out as a circular wavefront, moving straight lines away from it. And so as this is approaching me, what's happening is these sound waves that have a certain frequency, which means they're being produced here in a number of cycles per second, right? As it's moving toward me, those wave fronts are going to be hitting me faster than they're being produced, right? Because, again, if it's stationary, they're coming out at a cycle per second, but now it's moving toward you, and so you can just imagine that this one's going to hit, this one's going to hit, then this one's going to hit. And because it's moving toward me, it's the speed of the source plus the speed of sound, and that's going to be the relative sound that I'm going to hear, right? And the same thing happens as I'm moving, as the source is moving away from me. Now, these are moving towards me at the speed of sound, but the source is moving away from me, and so I'm going to subtract those two, and it's going to give me a different frequency, a lower frequency as it moves away from me, all right? So, hope that makes sense. Again, you've experienced it all the time as a frequency which we're now. There are lots of web pages. If you Google the Doppler effect, you can probably find a little animation that will show you and explain it with sound, probably better than I can draw it. And so I encourage you to do that. If this definition and explanation isn't making sense to you, Google the Doppler effect and see what you can find, and should help you out there. The formula that we're going to use is this formula here, and this is right out of your textbook. So if you go look in your textbook, I believe it's on page 408 of your textbook, it is the frequency of the detector equals the frequency of the source times the velocity of sound minus the velocity of the detector over the velocity of sound minus the velocity of the source. This is where it gets confusing because the velocity of sound is just v, the velocity of the source is vs, and some people get that s mixed up. Instead of saying velocity source, they say velocity sound, and they mix those two up. So just be careful. I've written them down here, so what each parts are. Detector, source, speed of sound, detector, source. And yeah, let's go to the other board. We'll do an example that uses this formula, and we'll see what we come up with. Here's our example. So it's kind of a weird example again. Don't worry about the stuff that is all around the important information, but here we go. We have a trumpet player sounding a note with a frequency of 524 hertz. Bonus points, if you know what note that is, you can send me an email. What note is 524 hertz? While traveling in a convertible at a speed of 24.6 meters per second towards you, what frequency do you hear if the air temperature is 20 degrees Celsius? So we have a bunch of information here. Again, we have our formula, but we know the parts of our formula. So here's what we're going to do. We want to find the frequency of the detector. So that's what we want to find. Now let's write down what we're given so we don't get things mixed up. And we are given the frequency of the source of sound. That's the trumpet, 524 hertz. Okay? We are given the velocity of sound. Now, here's where we want to come up with a little formula for the velocity of sound. Okay? The air temperature is 20 degrees Celsius. In your textbook, there's a chart of air temperatures, there's a chart of speed of sound at various temperatures. And in the reading part on the speed of sound, it gives you a formula that says that at 331 meters per second plus, and then it is 0.6 times the temperature. Okay. And so there we go. And if we do that, we will get a speed of sound of 343 meters per second. So there's our speed of sound. It also gives us the speed of the source, that's the car, or the trumpet player in the car is traveling at 24.6 meters per second. And the velocity of the detector, detector is you. You are standing still. At this point in this question, you're standing still, and so that's 0 meters per second. All right, let's put this information into our formula. We'll do that over here. So our formula is FD equals Fs. V minus Vd over V minus Vs. And let's plug in our information. We're going to have the frequency of our source is 524. I'm going to run out of room here. I'm going to move this. Give me a second. We all know how we figured this out. I'm going to do this. Okay, and increase this. Now we're going to do it here. Alright, so there we go. And let's fill in our information. So 524 hertz times the velocity of sound, 343 meters per second. Minus 0, so I'm not going to write that down. The velocity of our detector is 0. So I'm just going to leave that off there. Over speed of sound, 343 minus 24.6 meters per second. All right, we punch this into our calculator, and you should be able to get an answer. All right, so we have 564.5 hertz as our answer for that. All right, so, and again, that makes sense. It should be a higher frequency, right? If the source of sound is approaching us, we should be getting a higher frequency. Now, where does this question change if the trumpet player now passes you and is now moving away from you? None of the information changes, but it's a directional thing that does change. Okay? When the source is traveling towards you, you are going to subtract these two numbers. Okay? Because, again, we need to get, the denominator has to be smaller than the numerator in order for us to get a larger frequency, a higher frequency. Okay? So, if the source is moving towards us, we are going to subtract these two numbers. If the source is moving away from us, we are going to add these two numbers. Okay? Again, we can think of it as the formula doesn't change, V minus Vs. When it's moving towards us, the velocity of sound is positive. Right? It's moving in a positive direction toward us. As it's moving away from us, we can consider this as a negative 24.6. Again, the negative just being direction, that it's moving away from us. And if I put a negative 24.6 into here, it'll be 534 minus the negative 24.6. Right, giving us an addition there. And if we do that, we will get a lower frequency there. All right, so I hope that makes sense. There is 5 questions on page 409 of your textbook. That'll be your assignment. I'll put it on Connect for you, and ask any questions that you have. You can email me, and we'll go over some of those questions in a video tomorrow. Have a great day, and we'll see you tomorrow.